Let's explore some algorithms to code up row vector matrix multiplication via dot products. We'll start by reading the formal mathematical definitions and then make explicit connections between the math and the code. We begin by establishing that A must be a real valued matrix with m rows and n columns, and then we'll create a column vector x with m rows and one column so that the number of rows of x matches the number of rows of A. We define row vector matrix multiplication as x transpose times A, producing an output vector B, which our code is going to produce for us. That is going to be a row vector with one row and n columns. In this case, we're using a definition to define that output entry by entry, where the operation that we're using is the dot product. Specifically, we say that the kth entry of the product B equals to x transpose times A is calculated as the dot product between the kth column of A and the vector x. In mathematics, we write B sub k, in other words, the entry in row 1, column k of the product x transpose times A is going to be equal to the column vector x dotted with the kth column of A. Notice that the column index on A matches the entry number for the output we desire. If we look at an entry by entry definition, we can write this dot product using the summation I goes from 1 to m of x sub I times a I k, where the index on entries of x matches the row index on entries of A, and the column index on entries of A matches the entry number for the output we desire. And that's true for all values of k running across the row vector output that we want. We want to develop an algorithm to implement this. This relates to a previous video where we talked about the matrix column vector multiplication via dot products algorithms. If you haven't watched that, go ahead and go back to that. I'll link it to the top right-hand corner of this video. For those of you that have already watched this, I would pause this video now and see if you can generate a guess for yourself of what you think the algorithm should be before I present it. One of the best ways to learn is to guess what you think it should be and then correct your mistakes. My claim is you already have this one in you. You don't actually need me to tell it to you. Pause the video, try it for yourself, and I'll present it in just a minute. Now that you're back, I'm going to walk through this with you. When we did matrix column vector multiplication via dot products, we initialized y to be a zero vector of the size that we want. So my claim is probably over here for row vector matrix multiplication, we're going to initialize y to be a 1 by n. And then since we are doing m separate dot products, we wrote a for loop that went through the rows and calculated each entry of our output as the previous entry plus the dot product between the row and the vector. In the case of row vector matrix multiplication, we're going to do n separate outputs, not moving through the rows, but instead the columns. So my claim is it probably would be for k goes from 1 to n, and then the kth entry, so y1k, is going to be the previous kth entry, y1k, plus the dot product between not the ith row and x, but instead the kth column and x. That's my guess. Let's go ahead and confirm. Oh my God, look at this. We initialize y to be a vector which has 1 rows and n columns. That's the size of the output that we want. We go through the columns of that vector, each one coming from a dot product. The next entry in column k is going to be the last entry plus the dot product between x and the kth column. And now all of a sudden, I've used what I've learned before, actively test myself, and then check it. That's how I build really strong neural networks, through curiosity, courage, and active recall. Let's follow our habit. When we've done hard work in the past, let's reuse it. I'm going to go ahead and copy the previous row vector matrix multiplication file that I did. This one is not going to be via linear combinations. It's going to be via dot products. I call it sandbox because this is literally just for me and my explorations. Go ahead and open that. Here we're going to adapt this code. Remember, this was a way to test our algorithms more formally. I'm going to use the integer coefficient example that I calculated by hand so that I can really make connections between what I understand and what I'm doing. So I'll go ahead and uncomment that. Here we produce the MATLAB output. That's the same. I am not ready to do the BLAS Level 1 stuff because I'm still on the outside. But I am ready to do BLAS Level 2, which is to process this by entries. Nice thing is this is no longer via linear combinations. This is dot product. So I just changed one little bit of commenting there. This is BLAS Level 2. In other words, we're working with vector-sized updates. We're actually processing the entire data. What did we say here? Let me test myself. I know the algorithm is up here. Remember, one of the best ways to get good at any particular idea is to test yourself multiple times and just keep failing until you get it. So here, let's set y to be a 1 by n vector. That's the size that I want. In this case, I'm going to run through the columns of the output. So this is k goes from 1 to n. And then in the dot product version, I'm going to process each one individually, where I say that the kth value of y is going to be the previous kth value of y plus the dot product between x and the kth column of y. So this is BLAS level 2 because I'm not actually going to the individual entries. I'm processing this as an entire column vector. I think I've implemented this properly. Let's go ahead and check. Yep, okay, so now I'm verifying output, and of course it should be a row vector, and I can look at the norm. And when I run this, notice I get the exact same thing. Some of you at home might say, hey, that's not a super interesting example because it's super small. The point is that you don't need super large examples to get good intuition about problems, but okay, I'll mess with you. So let's go ahead and call this 100 by 100. We'll run. Notice that my error is down like 7 times 10 to the negative 14. That's pretty much the same. One of the ways that we're going to bring out the genius that you already have inside of you is to study multiple representations of the same idea. Here we're going to visualize how that algorithm works. On the right-hand side here, we have the math operation that we're trying to do, which is the computer science version of a row vector matrix product. We've initialized y, and then we're going to do a for loop to run through the individual entries of y. Over here is our for loop representation at BLAS level 2, where we're actually processing vector data. So the kth entry of y is going to be the previous entry plus the dot product between x and the kth column. Of course, this could be the d dot function that you coded up as part of this class, or it could be MATLAB's native dot function. Doesn't really matter. When we initialize this algorithm, we're going to set 3 data structures in memory. One of them is going to be a row vector y that stores the initial value, and then we're going to overwrite that with the desired value. Here I'm visualizing that as a column vector because it's hard to write a row vector across the screen. There's just not enough space. We also have a vector x, which is written as a column vector. And then we have a matrix A, which is visualized as a column vector. When we multiply x transpose, of course, in mathematics, we turn it into a row vector. When we're doing computer science, it doesn't really matter whether it's a column or row vector. What we need is the individual entries as we work through it. Similarly, we have our matrix A, which in our integer example was a 4 by 3 matrix. Once we have those data structures in memory, we enter our loop. The first loop iteration deals with the first entry of our output and does so by taking the dot product between the vector x and the entire first column of A, and then overwriting the new value in y with the old value plus the output of that dot product. Once we do that loop iteration, we increment the loop index. So now we move down to the second entry. We take the dot product between x and the second column, add it to the previous value and overwrite it. And then we'd go all the way to the end. In this case, the end is k equal 3. We take the previous value of y3, add it up to the dot product between x and the third column. We exit our loop, and the vector y now stores the exact output that we wanted. For those of you scholars that have actually worked through all of my videos, could you guess what we're going to do next? Could you guess, now that we have this BLAS level 2, where we're processing vector data to get the outputs, perhaps we want to replace the inner formula here with a BLAS level 1, where we actually go to the entry by entry version. Pause this video and see if you can guess what that inner loop would become to actually do the dot product at an entry by entry level. Welcome back. Let's actually work through this together and then verify our guess. So when I do this dot product, I'm actually going to run through each individual entry of x, which has m different rows. And I'm also going to run through each individual entry of the kth column, which also has m rows. So because I'm moving down the rows of the column, that inner loop goes from I equals 1 all the way to the last row, which is m. And then I'm going to guess that this is going to be x sub I times a sub ik, where I'm adding that product to the previous value. Let's check. Ding, 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 ding. I got it. I replaced that inner formula, moving all the way down to the entry by entry version with another for loop. So now this is a doubly nested for loop. And in that inner for loop, I'm moving through the rows of my matrix. So I index that with I, and I multiply the ith entry of x by the ith entry in the kth column of A, and then I add that to the previous value and I work down. Let's go ahead and code that up. I no longer need this BLAS level 2. Would be kind of nice to use the dot products here. So I'm going to copy and paste. I guess I could just type it too. It's not that big of a deal. I'll comment and then I'll uncomment this one because it follows the structure we've been using. This is row vector matrix multiplication via dot products, not via linear combinations. And then of course the loop order is actually different here. So I'm going to use the previous loop order as a start. And let me test myself again. I want you to see how many times I test myself during this. At home, I don't expect you to be able to get the answers as quickly as I do. If you're new to this, I'm hoping you're making a lot of mistakes. The point I'm trying to demonstrate is I do this all the time when I'm studying. I test, I correct, I try again. And in any given exercise, I've maybe tested myself 10, 15, 30 different times. And by the end of that exercise, I'm good. I kind of remember a lot about it. So the outer loop goes through columns. I'm trying to replace this formula with an inner loop that goes through rows. So in this case, I'm going to say for I goes from 1 down to the last row, which is m, should hit the end keyword as well. And then this is no longer the dot product. This is going to be the ith entry of x. In this case, x is a column vector, so I'm going to run down the rows. If x was a row vector, I would switch this. This would be 1, I. And then I multiply that by the ith entry in the kth column, and I move down. And the claim is now, let's run this. Same thing happens here. Oh, my errors are a little bigger here. You know what? This is a little bit too complex for my taste in the initial code up version. So I'm going to go ahead and get back to our integer coefficient data. And when I run, what are you worried about? Oh, something happened there. Oh, I see what it is. My matrix A somehow showed up as a comment, which is not good. So let's go ahead and bring this down. I'm not sure how that happened. And then I'll uncomment this part and we'll run it again. And notice that the algorithm that I've implemented produces the output I expect with a 0 error. I can do more interesting tests on that. I get some larger error, which is kind of cool. Leaves me to think what's going on inside of MATLAB. We'll get to that later in this course. For those of you math explorers that have been following along, you know I like to encourage you to visualize stuff. Here's a challenge for you. See if you can pause this video and recreate this visual for yourself in your own mind, given the work that we just did. Welcome back. We'll do that together. Over here is the math operation that we're working with, which is a row vector matrix multiplication, including an initialization. Over here is the pseudocode. We've got our two nested loops, doubly nested loops. The outer loop goes through the columns. The inner loop goes through the rows, and we update each individual output entry using our dot product written as a loop. When we initialize, we have 3 data structures in memory. We have our desired row vector viewed as a column vector for demonstration purposes. We have our input vector x and our input matrix A, and we're going to multiply x by A on the left-hand side. Of course, in math, this would be a row vector for the inner dimensions to agree, but in computer science, it doesn't really matter. We're just processing the individual entries of x with the appropriate entries of A. Once we have those sitting in memories, let's drop into our loops. Outer loop initializes as 1, inner loop initializes as 1. We update the first entry with x1 times a11, and we overwrite that in the first entry. When we increment the inner loop index by 1, we move down to the second entry of x multiplied by the second entry in column 1, because remember, this is the dot product between x and the first column. So I'm going to move down the entries of x and down the entries of the first column, each time updating the previous value. And I just keep going down until I get to the last entry in column 1. The first entry of our output now stores exactly what we desire. Now we increment the outer loop index and we repeat the process. x1 times a12 plus x2 times a22 plus x3 times a32. And then we go all the way down to the last one, which is the maximum value of the inner loop index. In other words, it's the m. Once we do that, we increment our outer loop index and we do the same process again, this time with the third column, x dot with column 3, update and store this in entry 3. So we move down those individual entries in the rows, and eventually when we're done with our loops, we exit, and now y stores our desired vector that we wanted to calculate, which was y plus x transpose times a. We kick out of the loops and we're there. This leads to the community challenge for this video. We've actually seen 4 different ways to do matrix vector multiplication. Matrix column vector multiplication via either linear combinations or dot products. Row vector matrix multiplication via either linear combinations or dot products. Each one of those had an implication for the way that we order loops and the way that we think about them. My challenge for you is to put away all of your notes, literally start with a blank slate, and see if you can generate both forms of the algorithm, the BLAS Level 2 and the BLAS Level 1 algorithms, just by thinking about it. And you can write the pseudocode on a piece of paper and then test yourself. This is a great way to strengthen that neural network that encodes these ideas. Once you've done that, create a quote-unquote cheat sheet, a single-page document that overviews everything that you learned for this that you can refer back to quickly. The process of creating a overview of this can be very, very helpful as you become more advanced as a way to kind of bookmark your learning. If you'd like, you can upload that and then share a link in the comments. I love that when students can share each other's work and kind of inspire each other to do deep learning as a team. The second community challenge is, given what we've learned about matrix vector multiplication, could you imagine what ramifications this has for matrix multiplication? The third community challenge for this video is, could you come up with a specification list for a matrix vector function that implements what we've seen and does so at production code level? So a function that is designed to be included in a library that you could share with the general public. Or if you were in the 1980s, you could design, I don't know, a software and call it, I don't know, MATLAB, and then sell subscriptions to academic institutions. Very interesting. You're learning the core algorithms upon which MATLAB is built. Pretty cool, right? With that, I thank you so much for your attention, and I'll see you in the next video where we implement production level code for matrix vector multiplication. See you there.